Hello again. So I want to now record another talk for a topic that's been keeping us quite busy, namely diffusion models, which I think is a really exciting topic in this larger field. So let's get right into it. We'd like to learn from data, so I'll keep that very short. But what now I think is really a crucial topic that motivates diffusion models is we not only want to deal with things like air, water, but we actually want to work with the inherent uncertainty in simulations, and for now I'll actually treat simulations as representatives also for observed data. Ideally later on, of course, we'd like to work with experiments, but for now I'll focus on the synthetic setting. And here we actually have inherent randomness. You can classify these uncertainties. Typically these are called aleatoric uncertainties, so we're really uncertain about a certain state. Imagine a measurement with some errors or an integrated quantity in a certain region. Then we really have to deal with not exactly knowing what might be happening in a certain sample. This is to be distinguished from so-called epistemic uncertainties, which are those that come from model approximation, and those could potentially be dealt with more data or adjusted models. So I don't want to say it's simple, but I want to focus on the first kind. And now I will actually mainly talk about dealing with these aleatoric uncertainties in the context of deep learning. So let's get right into it. I want to start right away with these diffusion models. What's this all about? You might have heard by now, or might not have avoided hearing about this. We're dealing with Markov chains. So we're setting up an auxiliary time evolution, if you want. So this synthetic time I'll call R in the following. So we're going from some input that you can see here is already a sample of a flow around an airfoil, and we actually destroy this, right, a Markov process, adding noise to it until at some specific time, virtual time R, there's nothing left. We really have no idea what happened initially with this airfoil. And then what we're actually interested in is the reverse stochastic process, right? Random noise is useful, but not too useful for making predictions about our real world. So we'd actually now like to turn this random noise sample into ideally our original state from before, or at least something from a similar distribution. So we're dealing with this in terms of the stochastic process and this reverse process. Reverting this Markov chain, this is actually what you'd like to learn. Right. On first sight, admittedly, it doesn't make too much sense why this is so interesting, but right, this is what I'll get to in the following. And just to show it in action, what essentially happens is we're starting with some random noise, right? This changes over our virtual time, it evolves, and ultimately we'd like to reduce the noise and get the kind of the data, the real signal hiding behind it out again. And right, this reverse process that we learn will actually in the following be symbolized with this green box with a little arrow inside. So this whole process, so keep this red part here in mind, will actually come up once in a while later on. Let's quickly introduce some of the notation. We're dealing with some quantity of interest, to y. The ground truth will be denoted by this y bar, given by some analytic or given function f, and we want to approximate this with a learned model neural network, typically given weights theta, such that we closely resemble this ground truth value of y. Now, simplest case, you can plug this into an L2 loss, minimize it, set your weights accordingly. Not easy, but by now I think we have quite a few tools to do exactly that. For these so-called denoising diffusion probabilistic models, which typically hide behind diffusion models, we now have this Markov chain with increasing Gaussian noise. And in a short form, you can see this as stepping in this virtual time R, and producing a sample yr plus 1 based on the previous yr and a so-called noise schedule. So actually reducing the contribution of our yr with, and show effectively we actually need square root of this alpha and then add 1 minus this alpha square root noise in the form of Gaussian noise called epsilon here with this noise scheduling alpha. It's a bit of an own science how to choose that, but you can imagine some kind of exponential decay or cosine decay sine function typically for changing the amount of this noise. And now that was too fast. What we now want to learn is the inverse of that, as mentioned before. So we'd like to actually turn a sample yr into one resembling the state at r minus 1. And for that, turns out we can actually now show that this reverse process can be formalized. We have a weighting of the previous state, a correction, noise reduction component given by the neural network in this case, f of theta, and we actually need to reintroduce a certain amount of noise, epsilon here, of this Gaussian noise. They all come with a factor. So we have beta for both the y, the f, and the epsilon here. I could normalize one out, but also for the exact values, I'd like to refer you to the according papers. The main takeaway message here is that according to the noise schedule, we can actually reverse this process given the right weighting. And this noise schedule is in a way a key here because we exactly know how the noise evolves. So we know for learning how much of the noise we'd like to actually have left when we are when we'd like to obtain the state at r minus 1. That's the main setup. Now we want to come to an example of why this is so interesting. So let's look at a relatively simple Renz flow example and directly compare a few methods that we have here from the past for dealing with such cases. You might be dealing now with something probabilistic. So we actually have a whole distribution of samples and we don't just want to get one out of them, but or one out as an answer, but we'd ideally like to get this whole distribution. Classically, you can use heteroscedastic models, which put a strong prior on our output, typically also approximating a Gaussian distribution, a parameterized one, so we can learn a mean and a standard deviation. Useful in certain settings. Bayesian neural networks have been around, have also been quite popular, but from our experience, actually don't work that well. Come back to that in a moment. And these diffusion models, or DDPM in short, is what we've looked at here for this airfoil setting, and that, because it's going to be in the focus, is worth elaborating a bit more. So especially for this airfoil case, now we have typically 3 different quantities of x, y, velocity, and the pressure. Those are a training time, or we apply noise to these at training time, such that the network can learn to actually reduce the noise. And then we actually additionally need to condition these on certain inflow. In training time, this is all treated together, but then for inference, we actually want to put in these conditions, for example, a certain angle of attack, a certain shape of the airfoil, and then applying the network over the course of these Markov chain steps ideally gives us back the different samples of our airfoil distribution. So this is a case we've also looked at in a previous paper. In a way, very simple setting, you can see these snapshots, something like a small image. So very easy to deal with, and also something that the other methods can potentially do. Now let's see how they perform. And now this graph doesn't look so interesting on first sight, admittedly, but this is actually now the key. So here we're looking at the standard deviation of these samples. Along x, we have different Reynolds numbers from pretty laminar, actually close to 0, not exactly of course, but something pretty small, on the order of a few hundred, up to order of millions Renz, so time averaged, Reynolds averaged, and along why we have the standard deviation of all the samples in our data. And here now, if you look at the black line, that's actually the ground truth. So not too surprisingly, increasing Reynolds number means we have more spread in the samples. If it's pretty laminar, the flow just doesn't vary as much. And now if we look at these different methods, the heteroscedastic model actually gets the standard deviation here quite right. You can see the slope of this curve is approximated quite well, but it actually cannot produce samples. What I've just shown on the previous slide, I'll show that in a moment, it actually doesn't get it back out. It only gives us these standard deviations. It just produces these per sample. So it's actually, unfortunately, in practice, not too useful unless you're really only interested in these parameters of a distribution you put on the posterior. The Bayesian neural network, that actually learns different instances of your network. And unfortunately, it comes with a KL divergence term, the lambda here, you can see at the top. And depending on how you set this, you can actually get out anything. So you can see these different levels here. We just tried this for 3 values, but the amount of standard deviation, the amount of variance you have in your samples, is determined by this factor you choose. And this is something you put in manually. So unfortunately, this is, to be blunt, useless. Right? You put in something, the model gives you some variant of that back, but it doesn't actually learn what should be in the distribution from the data. In contrast, DDPM here really does a surprisingly good job. It produces great samples, to be shown in a moment, but trust me on this for now. And it actually accurately learns just from the data across this range of Reynolds numbers how much the sample should vary. So it's the same model, it just receives same inflow conditions. The models are actually almost identical, but DDPM really learned here that low Reynolds number means samples shouldn't vary much. High Reynolds number means there's a lot of variance in the samples. And now I want to come to these gray regions on the side. Might have wondered already. These are actually the extrapolation regions. So this is data just used for evaluation. The training data is only the center white part. And DDPM actually does a pretty good job here, relatively flat extrapolation, even in the regions where it hasn't seen the data. Let's look at how this actually does in practice. So here are 3 models again, and these are now what you see here, different samples from the ground truth. So we actually sampled a RAND simulation, which for these really high Reynolds number flows actually does not reliably converge. And here just a few samples collected, similar to the training data, but now this is a test case. If we now just show one sample, heteroscedastic, right, just noisy. It doesn't know how to correlate. It cannot possibly reproduce a sample where we have a larger variation. In this case, one from the top. The BNN actually does better. This is now the better choice that approximates the median, but right, it's still noisy and unfortunately arbitrary depending on what you put in. If you choose the wrong one, it's quite bad. DDPM now produces a sample on the right. It really has the desired smoothness properties of the ground truth samples. And keep in mind, the ground truth is now a distribution. So all of these at the top are correct. And if you look closely, actually this sample, for example, nicely matches the fourth one here from the left. If you sample more, you'll actually also get some of the others. It really reproduces the whole distribution as given by the data, which is really what you want. So I hope this is the first data point to show that these models can really be useful in this context. And I want to quickly illustrate with the schematics here what the process, the learning processes behind it mean. So for a simple learned surrogate, as indicated by this yellow arrow, we just have one network evaluation. The heteroscedastic model learns the parameterization of our posterior distribution, and now indicated by this blue star, we have a stochastic process after it. So we get the mean and standard deviation value that we can sample. So the randomness basically happens after the model worked. The BNN is different. For that we have basically a parameterization of the distribution for a network. We can sample one network and then run our data through it. And the DDPM is approximating this Markov chain. So an important difference here is this arrow at the bottom, which is not so obvious. We have a certain noise process in here. this case, a noise contribution that you could call Z or so. And this we iterate on, so we actually do this many times potentially. It's more expensive. All the others just produce an output in one pass. DDPM needs to iterate. And the noise happens as part of this Gaussian sample distribution that is integrated into these Markov chain with this virtual time R. So as a summary, these are the key differences between the methods I've mentioned so far. And now I want to come to a topic that often keeps me and my group busy. So we're interested in not just steady state phenomena. I think this RAND setting is a great one for just testing whether it works at all, as you can sample the whole space very reliably. Just appeared at AIA. And for many other cases, however, we're really interested in time evolution. So, interesting question to ask. Can we actually use this process for time evolutions? Now, the goal of the network changes slightly. We don't just want to basically draw one sample from this posterior distribution. Rather, we want to condition on the previous input and then obtain a sample for the next time step, again, given the distribution, the different variations that could be realized for this next time step. And now the important thing to keep in mind here is now this icon for the reverse diffusion process is shown for every step along the way. For a time evolution, we now go through the whole Markov chain. For time 0, time 1, time 2, and now time 2, for example, is conditioned on time 1, but nonetheless goes through the Markov chain, potentially reduced one, come to that in a moment, for every step along the way until we reach some final time on the output. Now, what we found and what's really crucial for these models is to make them stable. And this is where I think the diffusion models really have a key advantage. I'll show that in a moment, but maybe let me first illustrate the conditioning a bit more, because here now this is actually quite important. We really want to make sure that for the temporal evolution, the model respects the previous time step. It was actually also used for the steady state RAND's case before, but in this case, the conditioning is even stronger here for the time evolutions. And at training time, each of the samples, called x here, right, we have some f of x, is actually dealing with the conditioning, shown in green here, and the data part. So they're treated together. Both of them are destroyed in this Markov chain. Both of them are denoised by the network, called P of theta here. This is training. We are also always just training with one step along this Markov chain, along the noise process. Right, so for the time setting, the conditioning is the time step t, and the output we'd like to get is t plus 1. We're just dealing with both of them together. The network actually learns to combine this information. At inference time, we just use the model trained this way, but now we'd actually like to prescribe the conditioning, right, that we know. We have the previous time step. So what we do now is analytically compute, given our xt basically, with the right amount of noise according to the noise schedule, the alpha from before, the right input, run our model to produce one for t minus 1, and then we basically just overwrite the conditioning at the top. So we're just keeping the bottom part of these samples. And that is enough to reliably condition these models on a certain input. And now the nice thing is, if you don't vary the noise, it's still deterministic, but if you draw different noise samples, you can actually now produce different answers. And here we have that for a transonic flow case over time. So this is already a pretty tough simulation that would be expensive to run. And on the top left now is a simulation, and all the other 5 are produced with different noise by a trained DDPM model. So you can see it is actually stable over time. I'll come to a variation in a moment. And these models, these were now 200 time steps. Oh, sorry. Initially, they're the same. So how we can see here. Then over time, they slowly start to deviate from the noise. Here's still quite similar. And after a few steps, now we can actually start to see certain differences below and above the obstacles where the shocks form. And then at some point, maybe around here, you stop and you just look at the shocks forming around the center part here. This region actually very different, but still matching the distribution as given by the ground truth. We looked at this in terms of a different spectrum of velocity amplitudes, for example. So the diffusion model, in this case, we call it autoregressive conditioned diffusion model, ACDM here, actually does capture this quite nicely. And one of the key advantages, I would argue, of the diffusion model is really its temporal stability. And this I also found a bit surprising, but we can now just use different learning approaches to learn this surrogate for the time evolution. And now if I play this on the left, again, it's a simulation. Then if you just look at the first one in the middle here, the FNO, in this case actually does perform quite badly. We also have a fairly advanced transformer architecture. This maps to latent space, does a time evolution there, has been shown to work quite nicely in other settings, but here for these cases it also does lose a lot of the detail actually quite quickly over time. It roughly matches the shapes, but not high quality. And now the most interesting, I would argue, are actually the last two here. So here what's denoted by UNet is actually diffusion unit, which has a couple of nice additions compared to the very classic unit. And what you can also see now, you can actually train the unit to do a good job for quite a few steps, but here around, I think before 100 steps, the unit actually starts to lose track of most of the important details, and actually at the end also does start to diverge. The diffusion model keeps the whole state and the right content of features here for the whole evolution, in this case 240 steps, but we did actually try this for much longer rollouts. We ran more than 200,000 steps. It's just stable. It does not blow up if you train it right. And in a way, I think this is really surprising. The diffusion model only was trained on single steps of this Markov chain. So it seems to have learned from that, or seems to have been forced to deal with the robustness and noise from the denoising task. And that also helps to stabilize the whole temporal evolution. Training the unit on just 2 steps is inherently unstable. If you put more effort into the learning process and unroll the unit, you can actually also stabilize it. But the diffusion model, interestingly, really learns this from the diffusion process itself. Yeah, this would be really interesting, for example, for the weather bench data set, which we worked on a while ago. And to summarize the state so far, I want to use some pictures of my son here. I hope he'll forgive me if at one point he notices that I've been misusing his photos here for my talk. So anyway, I think there are some really nice Easter eggs to discover here. The diffusion ones are really great in terms of temporal stability, despite really not being trained for this. And they enable this posterior sampling. So you suddenly have a probabilistic representation that nicely captures the different behaviors, potentially different modes and things that should happen in your data. So this is great. On the other hand, they have an increased computational cost. So you need to run through this many times. There are also interesting ways right now to speed this up, but they're more expensive. If you don't need the posterior sampling, it's actually questionable whether you need it, but nonetheless, this is an interesting direction. We've been working a lot with differentiable simulations, and this is another interesting component I want to get to here. If we have actually a simulator for our states, say states S, and we can compute a gradient, the Jacobian of P with respect to that input state, then we can, in a way, pretty seamlessly integrate it into a learning process. So if we have a simple network and you have the simulator, as shown here, you could, for example, nicely put it together by evaluating your solver on the output of a network and then computing some loss, then compute a gradient from the loss into your solver to the state, and the state being produced by a network to the weights theta. This is what happens in deep learning, right? And in a way, having this gradient very seamlessly integrates your solver into the learning process. So in a way, this is a well-established setting that we've looked at in other contexts, but does require a differentiable simulator. If you're interested in working without this, it's actually we just recently posted some new results and another talk on how to work with this, but it really, in general, is a good idea to integrate your solver. And you can look at this in different ways, whether you call it right, reverse mode or backpropagation, or it's some form of a join method. This actually is pretty much the same point to look at the combination. I want to cite Daniel Kahneman's viewpoint here. He said he passed away very recently. He describes how mind works in terms of some intuitive system 1 and a slow analytic system 2, and I think that's a nice viewpoint here. So in a way, the simulator gives us this analytic stepping, careful, guaranteed process, and the network a fast, intuitive correction of these states. And then over time, of course, you can get a baseline out of your simulator and augment this with a correction in the form of a network all the way along the chain. Now, so far, there's no stochasticity inside. In these schematics, there's none of these purple stars, but we have a simulator P, now in green, here that's interacting with the network, and that is repeated. So, look at some of our other videos. It's one of my favorite examples here. So we did this for turbulence modeling. Essentially, you can learn a closure term here for a shear layer case. And just to mention very briefly, if you unroll long enough, here in green, you can actually get a model that approximates the key quantities very accurately. And even with a tough comparison on the same hardware, same optimization, right? We don't see these orders of magnitude that some other people have with potentially apple-to-pair comparisons reported, but really apples to apples, you still see more than a factor of 10 that we can get out of these combined hybrid solvers that combine a network and a classical simulator. Yeah, so if you're interested in this, there are all kinds of examples by now that we've also made available on the web. But what's most interesting now, I think, is actually using the diffusion modeling perspective, and anyway, not too surprisingly, but it really also pays off to have this differentiable simulator work together with the diffusion model. And for that, I need to slightly change the viewpoint, because we looked at this in a NURBS paper last year. In a way, we have the same combination of a noising process, and in this case of physics, but a key change here now was that we now treat the time of this noise process as a physical time. So we don't have this orthogonal virtual diffusion time on top of a physical time, but now they're really aligned. That's an important difference. So really this now, the whole process that I've been talking about is now this diffusion process from before. The main idea is very similar still. We have a simulator and some corrector, in this case a score function that we learn. I'll come to that in a moment. And now we're looking at inverse problems. So we have an observation, say at a later state, and then we'd like to get an earlier observation, or one possible earlier state that could explain this observation, shown on the left-hand side here. And we can now somehow approximate this reverse time evolution, for example, by simply inverting a forward step. But typically this P does not just directly give us the answer, but we need a network to really span the different possible states and also to make this stable. I'll show that in a moment. So this is now a reverse physics and a correction function in the form of a learned score. The combination here now really involves the noise process in this chain just to make it clear in the schematic, you have now a differentiable simulator, a noise process in purple, and the network all working together to solve inverse problems. And yeah, for this stochastic PDEs, the corresponding simplest time integration step is the Euler-Maruyama step shown here. And for the derivation, we now actually use a score matching formulation with which we can formulate the inverse step from the Markov chain from before in this way. And now we actually have some terms that involve here the logarithm of the gradient of the logarithm of the probabilities, which gives us the learned, or will be represented by the learned score. So this is similar to the direct evaluation from before, and here we have a noise term with respect to the Z. If you're interested, I want to refer you to our paper here. So the reason for switching to this formulation is actually that we can really show that this combination is consistent. We are sticking to a proper score matching objective. This nicely fits into the theory, so this is in a way well-founded, which I think is an important starting point for experiments in this area. And this was actually better to do with respect to score matching, which you can closely correlate or can show it's equivalent to certain diffusion modeling formulations, so they go hand in hand. But yeah, I want to just point out that the derivation is definitely interesting. If you're interested, please take a look in the paper. I want to skip this here. Now, to show some really simple examples, now we're really looking at noise and our physical model together. And one nice toy problem is we have two different modes, 1 minus 1, that over time are destroyed into a neutral zero state, shown here by these red and blue curves. The corresponding score looks like this. We now actually want to reverse. We're basically drawing a sample at 0, and then we want to get either of those 1 minus 1s modes out. The already nicely learned score is shown here on the right-hand side. And if we now try to recreate this process, what we get out here is that if you do this with a one-step training, it's actually potentially unstable and explodes a bit too early. Whereas if we unroll the training, then basically taking the time evolution of the process into consideration, we can stabilize this, which is again something we show in more detail in the paper, but nice to show with this simple toy example. Yeah, now I want to show one specific case. The heat equation is an interesting one because here we can actually put in a known distribution and then basically destroy it with the diffusion operation. Simplest form of the heat equation, just it applies a Laplacian here, some strength. And on the first animation here for this P inverse, you can now see if we naively invert the simulator, the forward step, this blows up. It's essentially doing a sharpening operation without additional stabilization terms. This fails. The network, without any noise, gives us a probability flow evolution, which nicely matches the overall large-scale features of the ground truth samples. And if we incorporate the stochasticity in form of an SDE for the reverse time, then we really get out a nice distribution of samples here. We also looked at this for some simple flow cases here for learned time evolution, and notice that there's an inherent trade-off basically between a mean estimation in terms of this non-stochastic ODE version here, the probability flow. So the error for the SDE here in light green is actually higher than the one for the ODE, whereas the fine features and all the details are really nicely captured by the SDE, so it does fare better in terms of the spectral error compared to the ODE. Nonetheless, both yield very good approximations for inverse problems as the one shown here. Yeah, and with that I want to come to a bit of a set of conclusions. So I talked about these inverse problems, temporal predictions, and the complex distributions of the Rance flows, and the most important takeaway message is really diffusion models in a way give us a first reliable tool that can learn these complex distributions. They also give very good temporal stability, and they can then be used for downstream uncertainty estimation tasks. We are, for example, interested in visual captures. Here you can find our small capture setup that has a small fog machine. We can film the smoke clouds, and then here's a classic distribution, but this is a very good example of a highly ambiguous case. We only have very unreliably integrated measurements of these view rays, which are noisy, and working with tough data like this, I think is actually a very good case for diffusion models like this one, incorporating physics priors. So I think there are many really exciting questions left, and I'd like to thank all the students, especially Chang, Georg, and Benjamin, who worked on this. If you're interested, we also have this website on physics-based learning that captures a lot of these topics and will soon also include all these diffusion model examples. So stay tuned for updates here, please. Thanks for listening. Let us know if you have any additional questions here. But with that, I want to say goodbye and see you soon, hopefully.